Welcome everyone. So this is our 118th live stream geometry. We have a lot of people here with us right now, and today I am going to take some problems from the Balkan Math Olympiad Shortlist. So it's possible we might have done some of them long ago, although I think most of them are probably completely new. So if you'd like to join us in the future, feel free to email me at mgreenb801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. All right, so I will share my screen. Here is the first problem. So this is from 2019. And it was from the shortlist, so I don't think it was actually on the contest. So we have triangle ABC with circumcircle centered at O. I think part of the problem might be cut off here. So let's see. All right, so let me move this up a little bit. Let's draw the circle, and it's centered at O. We draw the tangent line to C, so maybe we want to put C at the top. And it intersects AB at the point D. So let's see. Draw that. This is point D. And it's well known that that forms the harmonic bundle with these segments and the symmedian, so I use that a lot. We draw the circumcircles of BCD, OCD, and AOB. So BCD, OCD, and looks like someone's joining, Leia. BCD, OCD, and AOB. It's a lot of circles. And they intersect the ray CA at points Q, P, and K. So BCD, we have to draw the whole ray. I'm guessing maybe, because it says the ray, so I guess we need to draw it like this. Okay. So this will be point Q, and looks like someone else is joining too. Leia. So that's Q. OCD, that intersects it at P, and AOB intersects it at K. It says the ray CA beyond A. So I mean, this isn't past A, but I don't know, maybe it'll, so let's see, P is on AK, K is on PQ. I think this works. The line PD intersects the circle BKQ at point T, so that P and T are in different half planes with respect to BQ. Okay, so this would be T. And we want to show T. That doesn't look right, so I must have made a mistake somewhere. So what did I do wrong here? So we have the tangent at C intersects it at D. And then the circumcircle of BCD intersects it at Q. OCD intersects it at P. And
at the very beginning, we have BC is greater than AC. So I think it's just the other intersection with BKQ.
Okay, so or which is the other, or T is? Probably.
Yeah, I think so.
Okay. All right. So yeah, we're kind of not really doing it the way the problem's set up, but I don't know. Should I draw the diagram, or we'll just leave it like this because it's probably the same proof, right? Okay. Of course, that would not work in an actual math contest, but we're just doing this for fun, right? Oh, are any of you having trouble hearing me? Okay. So let's check if that's true, that TB equals TQ. Yes. And not only that, it looks like that circle might pass through that point. So let's see if it does. Yes. Okay. So, all right. Now it says it's an acute triangle, and I'm kind of drawing an obtuse triangle here. So let's see. If I make it acute, then my picture will fall apart. So I'll leave it as obtuse and just say it's the same proof. It's kind of cheating, but oh well. All right.
I think it makes sense to invert around ABC.
Okay.
The point E you just drew is also on the symmedian.
Oh, okay.
Median.
Is it obvious it's on the symmedian?
I didn't understand which one.
Point E.
Yeah, that is obvious.
Is that
The DE are tangent. DE is tangent. That's why.
okay? And we know do we know that's tangent by an angle chase?
Because it lies on circle DCO.
Okay.
Yeah, because
That's
of
how we
90
defined
degrees.
it.
Oh, I see. So then that proves this is a symmedian because yeah, the tangents concur at D, so this is a harmonic quadrilateral, and so this has to be a symmedian. Interesting. Okay. So then we wanted to show that TE equals TB equals TQ. The problem doesn't make you show that TE is equal to them, but it looks like that's true. It looks like these concur. I don't know if that is an easy angle chase. Maybe it is. And do these concur? I don't think these concur down there. No. Okay. So yeah, CE is a symmedian. So CD, CB, CE, CA is a harmonic bundle. It's like Pascal is rejoining. And if these concur, which we still have to prove, we could project that onto this circle. And so that means DBFQ is harmonic. Oh, is TQ tangent? That's what it looks like. Let me check if that's actually true. But yeah, it certainly looks true that these are both tangent. Yeah. So maybe we could prove that. Because yeah, if they're both tangents,
Then we would have a harmonic bundle.
yeah.
So we would want to prove that dBFQ is harmonic.
Oh, but that's obvious that dBFQ is harmonic because basically if you project CD, CB, CE, CA onto this circle,
Yeah, I see it. So yeah, we have that it is harmonic. So yeah, we can characterize that point T on line PD. So we can say T is intersection of those two tangents. And then we want to show that we have that cyclic quadrilateral
okay.
BQKT.
Okay, so we can define T prime to be this point.
Yeah, but to be honest, this now looks just like an angle chase.
Yeah, I agree. Okay, so
Can you let like M be the midpoint of BC? Sorry, AB.
okay. Oops, sorry. So yeah, it's gonna lie on the circle because OCD is OED is 90. But yeah, so let's see if this is an angle chase. So
Yeah, it is. We have angle QKB. Wait. Wait, I'm not sure anymore.
all right.
Oh yeah, QKB is AKB is AOB, and QTB, because we defined it to be the intersection of these diagonals, is if we draw the circumcircle of BCQ, then it's just the angle like if we draw that circumcircle, circumcenter. I meant circumcenter.
Sorry.
Yeah. Then QTB is just QGB because that's a cyclic quadrilateral. But QGB is just 2 times QCB because it's the circumcenter, and we had on the other hand that QKB was also like was AKB was AOB is also 2 ACB.
Okay. All right. So I'm guessing. So yeah, you might have a different picture than me because yeah, I didn't draw it right. But like if you use direct angles, I think it's just all the same.
Yeah, I use directed angles.
Yeah. Okay. So yeah, this is an easy one. So okay. So first, since DC is tangent, by symmetry, DE is tangent. So since DC is tangent to ABC, by symmetry, DE is tangent to ABC, and then that means that CBEA is harmonic. And that means that AE is, or CE is a symmedian of CBA. And that means that I can write it like this: CB, CA, CE, CB is harmonic. And then we take that, we project it onto the circle CBD. Where did I, oh, forgot this. Okay. Projecting on a circle CBD. Basically, we have CDBF is harmonic. CDBF is harmonic. And then, oh, but we didn't show that these concur at a point. Well, oh yeah, I think there's still one more step, right? We have to show that these two concur on the circle.
So that it is an angle chase. So I will write it in the chat.
Okay. So yeah, maybe I can make that like the first step of this proof, and then just, all right. So, hey Anurag, thanks for joining. So if that's harmonic, let P prime on PD is the intersection of the tangents at D and B. The CBD. Let's think. And then we do the angle chase. So angle BKC is 180 minus BKA. This is 180 minus angle BOA. So we have this, which is 180 minus twice BCA. CA, and which is 180 minus twice BCQ, which is 180 minus BGQ. minus 2 angle BGQ, which is angle BT prime Q. BT prime Q, and that so I'll do it like this. So that means that B, so I see you put in the chat. I'm gonna look at it in just a second. So so BT prime KQ is cyclic and implies T prime equals T. T prime equals T, and that means that TB equals TQ. So yeah, we didn't even have to show it was equal to TE, although that's also true. And now I will look at the chat. So that is the angle chase. That shows that CE and PD concur on CBD. So CBD. All right. So yeah, not that hard of a problem. Let's leave this up here. Let's see. Maybe just for the people watching, I'll split this up into 2 lines. So how about this? All right, so CFD is CED plus PED. Okay, eventually you show it's equal to CBD. Oh, wait, oh, you defined F, basically you define F to be the intersection of these two.
F is the intersection of lines.
Yeah, and then you show from there that it's cyclic.
Yeah.
So I'll just write that, and then I'll move on to the next problem. So let F be CE intersect PB. Okay. All right, so this was a fun one. Of course, GeoGebra helped. You know, if we didn't have GeoGebra, it probably would have taken a little longer, but still not that hard of a problem. This one was actually on the contest. So I don't know if any of you already saw it or remember it. So
I solved this.
okay, is it hard, or do you remember how hard it is?
To me, it was pretty easy.
Okay.
But I think it needed 1 lemma.
Okay.
Which was known to me, but not too well known.
Do you mind if we try it, or?
No, I don't mind.
All right. So let's see. So we want CAX to equal Y8B. So I'm going to reflect this over the angle bisector. I don't know if there's a better way to do it, but that's usually how I do it. And so K and S are the perpendiculars from B to AX and AY. Oh, this actually looks kind of familiar. So I think we did some problem in the past where it's like if some 2 points are isogonal conjugates, then a different pair of 2 points are also. I don't know if that's the key to it, but we'll see. So
You mean isogonal line lemma?
well, it's a different lemma from the isogonal line lemma, but
Oh, okay.
yeah. So we want B to those two. So K and B to AX. So it's K and S, and of course we have a cyclic quadrilateral there. And then let me make this a ray. So we want C to AX and AY. Yeah, this does look very familiar. I think we probably solved it before, but let's see. So we would have T and L. Oh, this does look familiar. So I think it's something. We'll see in just a second, but I think I might have solved this on AOPS before, a long time ago. I think I might have an idea of how I did it. So I think there might have been a way just using projective geometry. Just trying to remember. Okay, so we want to show KL. Maybe I didn't label these right. Yeah, so let me see. K and S. Maybe I switched two of them. So this should be K and K. This should be S. Yeah, that looks better. Okay. I think there was some solution just using projective geometry. So let's see. So we draw line BC, and this is ST, this is KL. I think like I could let ST meet BC at a point like let's say D prime and KL meet at D double prime, and I could show some two cross ratios are equal. Let me see if that works. So I mean, so yeah, I'll draw the circles that we saw. But I don't even know if I really need them, but we'll see. So this is the altitude, AE. So like I could try to show DBCE, or I could call this like D prime, and then I could show it would be the same for KL. That's kind of my strategy. So I wonder, is this tangent? Let's see. No. Do XL, YK, and AE concur? It looks like it. Oh, so maybe DYEX is harmonic, or that would help. That's a good observation. Okay, interesting. All right, so I'm going to turn this into a segment. Actually, both of these, so I'm going to make them segments. So yeah, so that point of concurrency is not, I don't think it's the ortho. So the orthocenter of ABC or AXY? ABC. Okay. Let's see. Oh, somehow my tool didn't work.
We can show this concurrency if we can show that SLKT is cyclic.
Mm-hmm.
And that appears to be true.
Okay. XLKT, or sorry, what did you say?
SLKT,
Oh,
like
so-
the 4 feet of perpendicular,
okay,
and then it's just radical axes.
right. So yeah, that's the orthocenter. So to show, so SLKT to show that that's cyclic.
Oh wait, that shows a different concurrency. Never mind. In my picture, S and Y are really close together.
Okay.
But Johannes, you're right. You can solve the problem if you prove that SLKT is cyclic.
Okay, so are these triangles? Oh yeah, these are similar. So I think we can somehow use that similarity. Let's think. So by over yc, trying to remember that, because I think I solved this before and I somehow used similar triangles. So BSA and CTA are similar.
ASB and ATC are similar.
Yes, exactly. And I think there's even more similar triangles, like BYS and CYL are similar. So yeah, there's a lot of similar triangles.
So if we prove that ALC, yeah. So if we prove that ALC is similar to AKB, we can prove that by power of point that LSKT is cyclic.
Cyclic. Oh, I think that's yes. So I think by just using a bunch of similar triangles, we could show LSKT is cyclic. And then Johannes, you said that would solve it, right?
Yeah, but I was wrong. Like that shows that SK and LT concur on the altitude, but we wanted that YK and LX concurred.
Oh, but I think that might be a good first step, because if we show that these concur, so you showed that did you say SK and LT concur?
Yeah, on the altitude.
Altitude. Okay.
Just by radical axes, like the 3 circles we have.
But if that's true, then I think that would mean that ST D prime. I think that would mean that D prime Y dx is harmonic, and then if we let KL, I think it would mean, like, I think that would solve the problem. Because
Oh yeah, that makes sense.
yeah, because if we let ST meet it at a point, then that point would be harmonic with Y, D, and X. And if we let KL meet it at a point D double prime, then that would also be harmonic with Y, D, and X. Does that work?
How do you know it's harmonic?
Yeah, I think we're assuming the problem, right? Like to show that we use that D prime LK are collinear, right? Or how do we show that it's harmonic?
Oh, actually, never mind. Yeah, no, I think I got confused for a sec.
Let J be the midpoint of BC.
The midpoint of BC.
Yeah.
Okay. Okay, so we know that these concur. No, we have to show that. So okay, so I guess it's kind of the opposite. If we can show this is harmonic, it would solve the problem. Okay. Or you can prove XL and YK concur on AB. Interesting. So why is that true? D prime Y dx harmonic. I almost wonder if we could use the SARGs. Yeah, maybe we could use the SARGs. Like, I wonder if ST and SX meet on AB. It looks like it. Yeah, so if we could show ST and SX meet on AB, and then we could show that, what is it? LX and KY meet on AB. I think it would be
Oh,
like,
that's just the same statement, isn't it?
oh, by symmetry, yeah. So oh yeah, but that would mean that those are harmonic, which would make the problem really easy. So yeah. Is J the center of SKLT? Looks like it might be. Looks like it is. Let's see. Yeah, that's very interesting. So yeah, the midpoint of BC is actually the center of the circle. I don't know if it's easy to see.
I think you're right. You can use the Sarg's theorem to finish it.
You can use Sarg's theorem.
Yeah. So let BS and I forgot the point. BS and TC, yeah, intersect.
Okay.
And BK and CL.
Okay. Hold on one sec. BK and CM. Or BK and CL.
CL.
Okay.
And
Are these collinear? Looks like it.
yeah. So if we just, yeah, if we prove that they are collinear, then implies that BC, TS, and KL are concurrent.
Okay. BNCM is a parallelogram. Yes. So N and M are the vertices, and J is the midpoint of BC. Do we need I to be on that? Or is it obvious that I lies on that line? And do we even need that? So let's see. So we would have BSK and CTL. I think we do need I on it, right? So I could see why J lies on it, but I don't see it why I lies on it. But yeah, MJ and N are collinear.
I don't know if this is going to be important, but AM and AN are isogonal, just by the isogonal line lemma.
Okay. Yeah, so the isogonal line lemma, I mean, it says if you have points like this, I'm just gonna do a sketch of it, sorry. So if you have any 4 isogonal segments like this, and then you intersect PQ with RU and PR with QU, then the intersections of those are also isogonal. So let me see if I can make it look a little bit better. So it doesn't matter how long these segments are, how long or short they are, but if you do PQ intersect RU and PR intersect QU, then those 2 points will also be isogonal. That's what it means.
And in this case, our 4 points are BC and the infinite points perpendicular to AX and AY.
Yes. So it's kind of like a degenerate, case of it. Oops.
Okay, no.
If n prime is the reflection of n over KL.
Yeah.
So yeah, in that case, n prime m is going to be parallel to BC, and he said since suffice to show I n prime and I n are isogonal with respect to I. That's kind of interesting.
With respect to what angle?
I'm guessing maybe AIB is what he's saying. So maybe angle NIA.
Yeah, with respect to angle I.
Angle
Maybe me.
I.
Yeah.
Well, what is angle? What's angle I? Angle SIT or reflection with respect to with respect to KL, not BC. Okay. So okay. So IN and IN prime. So ILK, IST are similar.
But we don't know, like with respect to what angle are they supposed to be isogonal? I don't get it.
Yeah, I'm not sure. ILK. Oh, sorry. So what if is there anything special about this point right here? Basically, we would want to show KSOD is harmonic.
Do you have, can you do the intersection of KL and TC?
KL and TC. So that would be far away, right? Sorry, that point is so far away. What do you want to do at that point? Oh, maybe Yusuf got kicked off.
Yeah, so can you let KL and TS intersect?
KL and TS, yeah, so they would intersect on BC. I mean, we're trying to show they intersect on BC, right?
Yeah.
So I could intersect them, but then I would need to hide this.
Well,
You want me to do that?
as you wish. Yeah, so
It's tricky. Let's see. I like trying to show Ni, J, and M are collinear. We'd have to, so we need to show I lies on that segment. We know, so I is. It looks like a generalization of the orthocenter and like how the orthocenter midpoint and the antipode of A are collinear. It looks kind of just like a generalization of that. So this is cyclic, right? ASMT. And N, J, and M are collinear. We just need to show I lies on it. This is the antipode of A. Yeah, it's like a generalization of the orthocenter configuration. But yeah, so J is the midpoint of BC. It's not the midpoint of XY. That's what makes it a little tricky. So HJ, so if we draw the circumcircle of ABC, then HJ and the antipode of A would be collinear. But that's not what we're looking at. Maybe we could use Pascal's to show, let's see, Ni. We could see that SK and LT. J is the center of SKLT. LT is perpendicular to AB. Okay, so we could show J as the center of this, is what you're saying. Maybe we could use Brocard's theorem. So if
so just a second. So since AD is no. So this one after. So can you just scroll down a bit? I can't see it. Little bit. We denoted M. So since the AM is the diameter of the circle, so it implies that MST is similar to E. No. This one is it's this one. No, that's wrong.
Okay. But yeah,
Awesome.
maybe I was just thinking, basically, if we can show, what if we try using Brocard's theorem? So let's try that. So we know these intersect. And looks like we have another person joining. So we want to show that well, DI would be the polar of A, and AD would be the polar of D prime. So
I think I think I have a proof just using Menelaus's theorem on AYX, and we can just like compute the ratio that D prime divides YX, and that like it should just work. So we want to show that like AL over LY times XK over KA, and the symmetric thing that they work out to be the same thing. And well, AL over AK, we have similar triangles. ABK and ACL are similar, so AL over AK is just AB over, oh sorry, it's just AC over AB. And AS over AT is by like the same argument, just AB over AC.
yeah,
So we want to show that like LY over XK times YS over XT is AB squared over AC squared, and then we can use similar triangles again, like BX is similar to CX.
يوسف في واحد قال يوسف أن يراد كافي لاف إيفانوفيتش أوفيس ويجر باسكال راندومرز ستيفان سيبس ترينك
sorry, I'm having a little trouble hearing you. But Johannes, you were saying we could show that, like, I think it's like
intersect.
We could use Menelaus. Sorry. El Kadim, did you have a different solution?
Wait, how does it do?
I'm having a little trouble. I'm having a little trouble hearing you.
Let xy be 2 xy minimum x and y تركيب لانج تساوي لانج KS
Sorry,
are the
El Kadim.
from to a
El Kadim, do you have other people
يو
on with you?
S name is Sharaton.
Are you
Yes,
talking to other people? I might need.
Pascal believes me has a problem. T and L, the feet of perpendicular from C to AX.
El Kadim,
Algebraic
write it in the chat.
IG.
I'm going to mute you for the time being. All right. So, yeah, sorry about that. It's just, yeah, it's just too difficult. So, yeah, please type it in the chat if you have a certain idea. Just because, yeah, I feel like it's hard to hear your mic. Okay, so. Okay, so we'll try the idea using Menelaus and similar triangles. I wonder if there's a way to convert that to a proof using projective geometry, because most things using Menelaus have like a corresponding way of thinking about them. So like we have the cross ratio. For example, so I think it's just easier to see KL at first. So like if we want the cross ratio d prime or yx d prime, we could, let's see, we could project that. Yeah, like I see what you're saying using Menelaus. So d prime y over d prime x times xk over ka times al over ly equals 1. So we'd use that.
We use ABK is similar to ACL. And we use BYL is, wait, I'm confused right now. Sorry. Oh no, BXK is similar to CXT.
BXK is similar to CXT. And then there's another BYS is similar to CYL.
Exactly. And I think like one more, I think like ASB is similar to ATC or something like that. And then I think what we end up with is like BY over YC times BX over XC, and we want to show that that's AB squared over AC squared. And that's just like well known. That's just true.
Okay, because these are isogonal. All right.
So I think I know the lemma that Stefan said about. I'm not sure it's the same one, but I think it's useful.
Okay.
I remember I got this one from a small PDF. It's BC is the external angle bisector of DSL and K DT.
ADT. So it's the external angle bisector. So
Is it the same? I don't know, but I think it might help.
segment BC. It doesn't look like it's an angle bisector of KDT, right? Segment BC. So yeah, I'm not sure. But anyways, I'll start writing up Stefan solutions. So, sorry, not Stefan, Johannes' solution. Let's see. So Panos, I think, has a different way of thinking about it. But let me read what Panos says. So if D prime is the intersection and J is the center, then by Brocard, AI would be perpendicular to J D prime. Oh yeah, which, well, we kind of know AI because we know AI is perpendicular to BC. Like we showed I lies on the altitude from A to BC. Which, well,
how do we know that J is on BC? Like I think this proof works if we have that J is on BC. Did we prove that already?
Pascal said he had a proof of it.
Okay.
Pascal, do you
Nice.
know the proof that J is on BC?
He said in chat earlier that if we can prove that SK is perpendicular to AC and LT is perpendicular to AB, then he can prove that J is
The yes. let me see if he's still on. Looks like he left. Oh no, he's still on. So yeah, Pascal, do you remember the proof of that? That J is on?
So you define J to be the midpoint of PCs, and you want to prove it's the center.
Yes.
So first, to prove that SK is perpendicular to AC, we have that the angle ASK is ABK,
Yes.
and ABK is 90 minus BAK, which is 90 minus SAC. So SK is perpendicular to AC.
Okay.
So if you let's say the midpoint of AB to be like Z or something, then yeah, just maybe O is okay. Then you have that JZ is parallel to AC, and that is perpendicular to SK. So J lies on the perpendicular bisector of SK, and you have that J also lie on the perpendicular bisector of LT. So it's the center.
Okay. So it lies on the perpendicular bisector of SK and LS, or what were the two segments you said?
SK and LT. J lies on the perpendicular bisector of both that segment.
Okay. Because ZJ is parallel to AC, so therefore it's perpendicular to SK. And then ZK is equal to ZS, so JS is equal to JK. Okay, so yeah, that proves that J is the circumcenter of this. And then by Brocard's theorem, I see, then D prime would lie on this, and that would solve the problem, right?
Yep.
Okay. So yeah, Johannes had an interesting solution, but I think I'm going to go with this just because it would require less calculation. So, all right. So first, we have a whole bunch of similar triangles that show that SLKT is cyclic, right? So I'm going to write them down on a piece of paper, and then I'm just going to type them up. So let's see. Okay. So we have ALC is similar to AKB, I think. So ALC and AKB. And then we have ASB and ATC. I think that might be enough. Yeah, okay. And so then that would show that SLKT is cyclic. I'm kind of assuming a bunch of things here, but so ALC is similar to AKB, and ASB is similar to ATC, and using the ratios, I'm just gonna abbreviate here. We would get SLKT is cyclic. Is that true? So we have AL over AC is AK over AB. That's one ratio, and then we have AT over AC is AS over AB. And yeah, if you divide those, I think you get it, right?
Yeah.
And so, okay, and power of a point. So let KL and TS intersect at D prime. And then by Brocard's, so first of all, we need to show LT and KS intersect at I, or intersect on altitude. Actually, do we need that fact? I'm not even sure if we do. Well, yeah, I think we do. Because the altitude's perpendicular to BC. Okay, so how did we show that? Oh, by the radical axis, that was the radical axis theorem. So by the radical axis theorem, LT, KS, and AD concur. At a point I. All right. And by Brocard's theorem, okay, now we need to show, so let J be the circumcenter of SLKT.
No, J is the midpoint of BC.
Oh, sorry. Let J be the midpoint of BC. Then we're going to show it's that circumcenter. So, so we're going to show it lies on both the perpendicular bisector of KS and TL. So Z, say and Z the midpoint of AB. Let's see. So then so ZK equals ZS. So then JZ is parallel to AC, which is perpendicular to KS. So the fact that AC is KS, and the fact that AC is perpendicular to KS, I think that's yeah, I mean, I'll just say by an angle chase. And then okay, so that implies that so since ZK equals ZS, then JK equals JS. So ZK equals ZS. Okay, but wait a sec. I'm still not sure if that's the last step, because basically, oh yeah, then so similarly, JL equals JT, and so J is the circumcenter. Yeah, because we knew it was cyclic. So J is the circumcenter of SLKT. Is that right? And then once we know that by Brocard's theorem, JD prime is perpendicular to AI. So that implies that D prime lies on BC. BC, and that means that KS, KL, and ST intersect on BC. All right. So that solves the problem. Did we miss anything here? I think we got it all. right?
Yeah.
All right, that was fun. So let's move on. This is the third problem. So we have a centroid here. This one looks like it might not be as hard. I have some harder problems, but let's see. It has a
Can we
centroid.
try?
Let's try it. So, so we have an orthocenter, centroid. So yeah, I'm gonna. Yeah, it looks like we have a lot of 9-point circle stuff here. Use some OP6. I might take a look at it later. We'll see. So let's see. So this is H, and whoops. This is H. Let's draw the centroid. That would be G. So we're gonna have to rename some stuff right now. Let's call it K, and this should be G, and this we'll call R, and circle. Let's draw the circumcircle. So B and M are the intersections of AH. What happened here? AH and AG. So D. Oh, this is M. Okay. MH and DG intersect the circle at P and Q. So MH, that's and DG intersected at P and whoops, sorry, I'm just doing terrible today. This is P and this is Q. And we want to show that PD and QM intersect on the circle. So yeah, this can't be that hard, or it doesn't look like it should be. So yeah, maybe we'll just solve it really quickly. So let's see. So PD and QM. We want to show they meet on a circle. Let's see. One sec, guys. I'll be right back. All right, I'm back. Sorry about that. So PD and QM. We could draw the 9-point circle if we want. I don't know if it helps.
So I have 2 observations, and I can prove like one of them. So first of all, like AQ is parallel to BC. That like doesn't look too hard to prove, but I haven't really looked at it. And also,
yeah, I think that's just. Anyways, go ahead. Sorry.
and also we have like the point we want to show that the intersection point is on the symmedian, and for PD I can prove that, but for actually.
If you prove that AQ is parallel to BC, and I can finish up the problem for you.
Yeah, I think then we can just spam ratio lemma.
Yeah, P is the Q point. So okay. So G is 2/3 of the way from A to M. And but basically if we draw, let's say we define Q to be the parallel, we would want to show that AQ is twice DM, and then that would solve the problem, right?
Oh, I think it's
obvious.
just
Yeah.
I think it's just the like the homothety at G with like ratio -2.
Exactly. So AG is twice GM, and it's also obvious that AQ is twice DM, because if you drop a perpendicular from Q, by symmetry M would be the midpoint, right? So AQ is twice DM and AG is twice GM. So these triangles have to be similar, AGQ and GMD, and so those have to be collinear, right? So that explains that.
Can you intersect BG and MQ?
I think we're just done now. We can just like spam ratio lemma.
Maybe
not the power
MK
ratio.
is faster.
Let's see. Did you say PG and MQ?
No, PD and MQ. PD.
Oh, PD and MQ. Okay. So to that point.
Can you label that point?
Yeah.
So you have that the angle DJM is 180 minus JDM minus JMD. And JDM is like PAM, because that's cyclic.
Okay.
And JMD is QMC, which is MQA, and that's MAQ. So that proves that J lies on the circle.
Okay. Does MAQ equals MP, or okay, so so DJM is 180 minus this angle, which is 180 minus this angle, like AQJ. Okay, minus and then this angle JDC. I think he said it was PAM. So,
yes, PAM.
Because this is cyclic. So let's think. So I guess that's cyclic by Rimes theorem. I think it looks like it. Yeah. So so it's okay. So I'm just going to write it out on paper with angle chases. So DJM is PAM. So that's angle
And
PAM
make it as possible.
minus, okay, minus angle AQJ, which is so that would be PAM minus MAQ. Okay, so it's PAM minus MAQ, and then where, just trying to think what MAQ is isosceles, yeah. So I have it all the way down to that it's equal to angle PAM minus angle MAQ, is that right? Or
That's like, that is 180 minus PAM minus MAQ.
okay, so it's 180 minus PAM minus MAQ.
And that is PAQ.
Okay. Which is angle, yeah, 180 minus angle PAQ. Okay. Yeah, somewhere in my angle chase I got confused. Let me think about it. 180 minus this, then minus. Oh, okay. I see what I did wrong. So 180 minus AQJ. Okay, so I'm going to type it out. So angle DJM let the parallel from A to BC meet ABC at Q prime. All right, the next problem is going to be harder, or it should be. Then okay, so then let D prime, well, by symmetry DM is half of AQ prime. And GM is AG over 2. So that implies that Q prime, G, and B are linear. And that implies Q prime equals Q. And then let PD and QM intersect at J. And then we can just do an angle chase. So angle BJM is equal to 180 minus angle AQJ minus angle PAM, is equal to, let's think about this. So yes, and then AQJ is equal to MAQ. So this would be equals 180 minus angle MAQ minus angle PAQ Wait, is that right? No, PAM. Which is 180 minus angle PAQ. And that implies J lies on ABC. And that means that PD and QM intersect on the circle. All right. So Johannes, were you thinking about using the power ratio lemma or something?
No, the ratio lemma. It's a different thing. I don't know if the name's that common.
Okay.
But the lemma is if we like call for any point x, we call like bx over cx, we just call that like f of x.
Mhm.
And then it happens that if we have like 2 points, say in this case like p and j, for example, and they both lie on a circle through b and c, then we know that f of d is just f of p times f of j.
Yes, so I learned that lemma. Someone from Vietnam on the session taught me that. So it's like BP over CP divided by J, BJ over CJ equals BD over CD or something. Or
Exactly.
okay.
And we can use that to calculate a bunch of ratios. For example, well, BQ over QC is just CA over AB, right?
Yeah.
And then
BM
f of
over M
j.
is 1.
Yeah, exactly, because f of m is 1, then f of j is just also f of a, or I guess negative f of a if you include like signs. And then we can also, now we just need to show that like f of d divided by f of p is also like f of a, or like plus minus f of a, whatever. And to do that, what we can do is we can show that, wait. Oh yeah, we know that f of p times f of a is the same as f of f times f of e, because they intersect on BC. We can like apply like the lemma twice, and the intersection point has the same value of f. And then, well, we can use Cheva's theorem to finish, like to show that BD over DC, that's just BF over FA times AE over AC. And if we multiply that all together, we get that, well, the point of intersection of PD with the circumcircle is also like this point on the symmedian.
Sure thing. So I think you use that lemma 3 times. So the first time you use it with Q, M, and J to find BJ over JC, then you use it with P, D, and J to try to prove that they're collinear, but then you need some other ratios using Cheva's theorem.
Yeah.
Interesting. All right. Yeah, that's a pretty useful trick. Yeah, I feel like that probably makes a lot of these problems easier. But yeah, in this case by itself, yeah, the angle chase is probably easiest. All right, so this one I think is harder, supposedly. So, so we have a triangle with circumcircle omega, and the angle bisector, we want to see where